Dr. Ralston mentioned earlier that we're going to be able to facilitate solving differential equations using Laplace transforms. And what we're going to do is use Laplace transforms to get rid of the derivatives, then do some algebra and take an inverse Laplace transform, and have our solution y of t if we have y as a function of t. And we're going to be using this theorem right here that you'll notice we take Laplace of f prime and get down to simply s Laplace of little f minus little f at 0, which has no derivatives. So let's take a look at the proof here using integration by parts. The Laplace of f prime by definition is what you see right here. We're going to let u equal e to the minus st and v equal f at t. So du is, we're taking derivative with respect to t here, minus s e to the minus st dt. And of course, when we multiply u times v and evaluate it from 0 to b as b goes to infinity, you get what we see right here. And we can write that as f at t over e to the positive sb, but f at b is of exponential order, so that's going to go to 0. The denominator is going to go to infinity faster than the numerator there, so that goes to 0, and we're left simply with the lower limit minus e to the 0 f at 0, so we just have an f at 0 there. And of course what you see for the v du part of that integration by parts is simply s times the Laplace of f at t. So all we have left here is s Laplace f at t minus f at 0, and so we have eliminated the f prime. In a minute we're going to see how to work with higher order derivatives, f double prime and so forth, but first let's look at how we can use this theorem right here.
And we can use it to find the Laplace transform of cosine bt because we know the Laplace transform of sine of bt. If f at t is sine bt, the derivative, f prime, is b cosine bt. So the Laplace transform of f prime is s, capital F at s, minus f at 0. So that's s times the Laplace transform of sine of bt minus little f, which is sine, of 0, which is 0. So that's s times b over s squared plus b squared. But you can move a constant outside the Laplace operation. So on the left, we have b times the Laplace transform of cosine bt is equal to what we have on the right. So we're left with the Laplace transform of cosine bt is s over s squared plus b squared.
Let's use that same formula for f prime, Laplace of f prime at t, to find the Laplace of higher and higher order derivatives. First we're going to start with f double prime. We're replacing f prime with f double prime, and of course f double prime is the derivative with respect to t of f prime at t. So here we've replaced f prime with f double prime, replaced f with f prime, as you see right here. We've used that same formula here and we get this form right here. But now we replace the Laplace of f prime with what we got previously, which you see in here. So we've got s squared Laplace of f at t minus f at 0 minus f prime at 0. So we end up with this formula for the Laplace of the second derivative, s squared capital F at s minus f at 0 minus f prime at 0. And we can keep going higher and higher here and find the Laplace of the nth derivative of t, as long as the function and all the way up to the n minus first derivative, all those are piecewise continuous, and all those are continuous, and the nth derivative is piecewise continuous on the interval from 0 to infinity, and every one of those functions is of exponential order, then we have what we can prove by induction, this formula right here for the Laplace of the nth derivative of f with respect to t.
So let's find the Laplace transform of a given differential equation with specified conditions at t equal to 0. So the differential equation we have here is y double prime minus 2y prime plus 5y is equal to minus 8 e to the minus t plus 3 cosine 2t, and our initial conditions are at t equal to 0, y is 2, and the first derivative is 12. We take the Laplace transform of the entire differential equation using the fact that it's a linear operator and we can move the constant outside. So we're going to have the Laplace transform of y double prime minus 2 times the Laplace transform of y prime plus 5 times the Laplace transform of y is minus 8 times the Laplace transform of e to the minus t plus 3 times the Laplace transform of cosine 2t. We know how to take the Laplace transform of the second derivative. So that's s squared capital Y of s minus s little y at 0 minus y prime at 0. Then we have minus 2 times, and what you see in parentheses is the Laplace transform of the first derivative, s capital Y at s minus y at 0, but that's 2, plus 5 y at s, and that is going to be equal to, on the right-hand side, we know that the Laplace transform of e to the minus t is 1 over s minus a minus 1, or s plus 1, and the Laplace transform of cosine 2t is s over s squared plus 2 squared, or s over s squared plus 4. So when we substitute in the 2, the 12 for the initial conditions, and then I want to solve for the Laplace transform of y of t, capital Y at s. So when I collect on the left, I have y at s times s squared minus 2s plus 5. All of the other terms we're taking to the right-hand side and combining with the two terms that are already on the right-hand side. And so I can solve algebraically for the Laplace transform of y of t, capital Y at s.
Remember the first fundamental theorem that the derivative with respect to x of the integral from a constant to x of f of t dt is simply, all we do is replace the t with x, and it's f at x. So now we're going to look at the derivative with respect to t of the integral from 0 to t, f of tau d tau, and that's f at, we replace the tau with t. And we're calling that integral g of t. So the derivative of that, g of t, is simply f at t, and g at 0 is the integral from 0 to 0 of f at tau d tau, which of course is 0. And you know the formula here for the Laplace of g prime at t, it's s Laplace of g at t minus g at 0. But our g at 0 is 0, so we have s Laplace of g of t is equal to Laplace of f at t. We divide both sides by s, and we get this formula that you see right here. But g of t is the integral from 0 to t f at tau d tau, so that is equal to 1 over s Laplace of little f, or 1 over s capital F at s. So let's take a look here at the integral from 0 to t of cosine of b tau d tau. That, of course, integrate cosine, you get a 1 over b sine of b tau there, evaluated from 0 to t. Lower limit sine of 0 is 0, so we simply have sine of bt over b. The Laplace of sine of bt over b, we can bring the 1 over b out in front, and we know what the Laplace of the sine of bt is. It's b over s squared plus b squared. So if we multiply that by s over s, we have 1 over s times s over s squared plus b squared, but you recognize s over s squared plus b squared as the Laplace of cosine of bt. So the Laplace of the integral from 0 to t of cosine of b tau d tau is 1 over s Laplace of cosine of bt. We just replaced the tau with a t there. Or the Laplace of the integral from 0 to t f of tau d tau is equal to 1 over s, the Laplace of little f of t, which is 1 over s capital F at s.
So now, remember, the Laplace transform of the derivative of f at t is s, capital F at s, minus f at 0. If f at 0 is 0, that's simply s, capital F at s. And you just learned that the Laplace transform of the integral from 0 to t, f of tau d tau, is 1 over s, capital F at s. So that means taking the derivative in the t domain is equivalent to multiplying by s in the s domain, and integrating in the t domain is equivalent to dividing by s, or multiplying by 1 over s, in the s domain.